Welcome to GATE CSE. Today we'll understand the concept of eigenvalues and eigenvectors. Before we try to understand the procedure to find these values and vectors, let us understand why. Okay, why we need to find it, how they help. So let's begin. See, in the real world, so there are many problems you solve. So why you are learning linear algebra? Linear algebra helps us to find the solutions to any of the complex problems. In that, the most important topic is the concept of eigenvalues and eigenvectors. Okay, let us understand what they mean and how they help us. See, you usually take a system of linear equations, for example, and then try to eliminate some of the dependent rows. See, the entire concept of matrices using is to reduce the number of solution space. Okay, so there will be say like 1000 by 1000 matrix. So do we really need to process all the 1000 by 1000 elements? So that is the question. So the main idea behind the linear algebra using the concept of matrices is to reduce your computations. Okay, find the better way, better algorithms by reducing the number of elements or number of elements in your solution space. Now let us take an example. Let's take you are solving a real world complex problem, and then you want to study some properties of any object. Okay, so to understand that, let us understand your concept of a vector. I'm not explaining any in-depth concept of vectors here. Already you have learnt in your high schools or in your intermediate. So what is a vector? You just represent a vector by an arrow like this. It has a vector has magnitude and direction. The vector has both magnitude and direction. So magnitude means usually we'll say what is the length of this vector. Direction means which direction it is pointing to. Okay, some example north. L is the length. This is the magnitude. So vector will give me both. Vector will give me both magnitude and direction. Now, when you study a real world concepts, let us say you have some matrix A. So okay, you have some matrix containing elements A. This matrix A may be your solution space or whatever your problem you have modeled it as a matrix. If I apply this matrix for the vector B, okay, let us say this vector has both magnitude and direction. So what exactly means? Suppose I have an object, some object is there. So I am applying vectors. You can consider it as a force. This is one vector, there is another vector, there is another vector, V1, V2, V3, V4, V5, something like this. Okay. Now, when you apply the matrix, see, a vector changes both magnitude and direction. Okay. So your study or understanding of the system becomes unstable. Unstable means, see, when I apply something, it transforms. So that we usually call it as linear transformation. The linear transformation, it happens. So when it happens after applying this matrix A, so what will happen? See, for this example, these vectors say they will change. Okay, they will change in magnitude also. They may change in direction also. Okay, because vectors define both magnitude as well as direction. So now what happens? It is difficult. It becomes unstable. Means it becomes difficult to study the system, because if I do some transformation, I'm not able to grasp or understand how the system is behaving in the real world. So for that, if there is anything such that if I get applying on this, if I get some vector, okay, some vector, say lambda is a scalar value into V. V is the vector. Okay, let us say. So if I apply a matrix A on a vector V and I get a lambda into V, where lambda is my scalar value and V is my vector, where this vector changes in magnitude only and no change in direction. No change in direction. That means what? I'm just understanding the system. The system is stable because whatever I do, it's expanding in terms of magnitude. Okay, I can measure it. Now there are no direction change here. So that means my system becomes simple to study now. Okay, it is changing in only one dimension, that is magnitude. So that we call usually a stable system. So the process of finding this, we call it as the eigenvalues and eigenvectors. To find the eigenvalues and eigenvectors. So what is this lambda? Lambda here, scalar, we call it as eigenvalue. This V, the vector which does not change direction, we call it as eigenvector. So this is why we study the concept of eigenvalues and eigenvectors. Now where they are applied? There are many applications. In my textbook I have given many applications. Let me explain one of the applications. So let us say I have a matrix. Very big matrix, say. So I found I've studied a system and I've generated a matrix, say 10 power 6 into 10 power 6. So many elements. So 10 power 12 elements are there. Now, when I study this, when I find the solution, suppose say I implement this algorithm or the code on my computer. That means what? To find or to solve this, I need to do say 10 power 12 computations. I have to check all these elements 10 power 12. So this becomes what? Computationally intensive. That is the goal of linear algebra. Intensive. So what is that? Now this is matrix A. Now I am saying, can I find a matrix, okay, B which is transformed from A and which has less elements in it? So that basically what I am doing, I am transforming this dense matrix. Dense means almost all the elements are non-zero. Okay, sparse means very few elements are non-zero. Most of the elements are zero. Then if most of the elements are zero, then what? My processing becomes less intensive. That means it will be faster also. It will be more efficient than the dense matrix, using the dense matrix. So this is where we use the concept of finding the eigenvalues and eigenvectors. So this concept also we'll learn in this syllabus. Okay. So now with the basic understanding of why and its applications, let's begin the procedure now. So how to find these eigenvalues and eigenvectors from a matrix. So let's see a formal definition. So let A be a n cross n matrix. The scalar lambda is an eigenvalue of A if there exists a non-zero vector such that A into V equal to lambda V. So that's what I said. You are transforming into a given matrix into another vector. This vector V is called here eigenvector and lambda is called eigenvalue. So basically your lambda value, eigenvalue, indicates the scale of your vector. Okay. Now how to find it? Finding it is simple. So first you have to find the characteristic polynomial. So characteristic polynomial means you have to find a polynomial equation using your eigenvalues and then find the roots of that polynomial equation. So how will you find? So AV, okay, matrix A applied over vector V equal to lambda into V. So Find lambda, I will take minus lambda v, that becomes equal to 0. So this implies, if I take out v common, a minus lambda into I is equal to 0. So now how will you find v? So this is to find the determinant of this. So a minus determinant of a minus lambda I equal to 0. So for this you get a polynomial equation, say polynomial equation with lambda as a term, say lambda square minus 3 lambda plus 2, something like that. Then you can find the eigenvalues easily. Once you find the eigenvalues, you will find the eigenvectors. So first, what is the procedure? Find the polynomial characteristic equation. From that, you solve that equation by equating it to 0 and then find all the possible eigenvalues. So if the polynomial is of order n, so you will have n eigenvalues. That is the meaning. Then how to find eigenvectors? Once you get your eigenvalue, you solve this equation to get your vector v. That is the eigenvector for each eigenvalue. For each eigenvalue, you can get one eigenvector. Okay. So let's see an example. Find the eigenvalues and eigenvectors of this given matrix. So what is there first? First you find the polynomial equation in terms of eigenvalues. So this is a minus lambda I, determinant of a minus lambda I is equal to 0. What is a? So first you find the matrix A 2 1 1 2 minus lambda is a scalar and then I. So 1 0 0 1 2 cross 2 matrix. So this will be 2 minus lambda 1 and then 1 then 1 2. 2 minus lambda. Okay. So what I'm doing is multiplying this inside and then subtracting. Okay, so I get this. So you take the determinant of that. So determinant of 2 minus lambda 1 1 comma 2 minus lambda. So this is my polynomial equation. What I will get? So you just find the determinant of this. So 2 minus lambda whole square minus 1 is equal to 0. This is my polynomial equation. Now you solve that polynomial equation. 2 minus lambda square is equal to 1. So 2 minus lambda is equal to plus or minus 1. That implies lambda. There are two values possible, right? So lambda will be equal to, say lambda 1 is equal to 1 and lambda 2 equal to, you get as 3. Okay, if you find the lambda. Now, these are my eigenvalues. So there are two eigenvalues because it is quadratic, x square, lambda square. So these are my eigenvalues. Now how to find the eigenvectors? So for each eigenvalue, I will get eigenvectors, one eigenvector. So first we'll start with lambda 1 equal to 1. How will you find? So a minus lambda I into v should be equal to 0. Is this? So same thing again. So what is a minus lambda I? So lambda here is lambda 1 equal to 1. So instead of that you put 1. So in this equation, you may 2 minus lambda 1 1 1 and 2 minus lambda 1 matrix into this v is equal to 0. Now, So what is lambda 1 value? You already know. So put that lambda 1 value. This is 1. 2 minus 1 is 1, 1. This is 1 and this is 1. This into V. Now vector is the column vector. So how many variables will have? The 2 cross 2 matrix. So what is it means? The 2 cross 2 means this is one column vector, right? So two values are possible. So let us say x1 and x2 is my eigenvector. x1, x2 is equal to 0. In the next chapter again we'll learn system of linear equation. We will be solving like this. Now what will be the equations now? So this row and this column, multiply this row and this column, forms another equation. That is, the first equation is x1 plus x2 is equal to 0. This is the one equation. Then another equation is this. Again same, x1 plus x2 is equal to 0. So both says what? X1 is equal to minus x2. Right? Now, how to find the vectors? Let's say we'll put x1 is equal to some value t. This is call it as parametric value t. And then x2 will be equal to minus t. So what will be my eigenvectors? Eigenvectors will be v is equal to x1 is t, this is minus t. That means t 1 comma minus 1. So this is my eigenvector. So t here means what? T here scales. Scale means if I put t equal to 2, it will be 2 and minus 2 is another eigenvector. T. It's a integral multiple of t. That is the meaning. Similarly, if I take lambda 2 equal to 3, what will this matrix will be? 2 minus 3 till minus 1, and then you will get 1 minus 1 into x1 x2 is equal to 0. Now, what are the possible equations? I'll write it here. So for this I'll get minus x1 plus x2 is equal to 0 is one equation. Another equation is x1 minus x2 is equal to 0. That implies what? x1 is equal to x2. Let us put t is equal to x1 equal to t. So the eigenvector will be b is equal to t and t. This is nothing but t. The eigenvector is 1, 1. So this is another eigenvector. This is how you have to find. And where for both the condition t should not be equal to 0. You can take any negative value, it can take any positive value. It's a scaling. T is not equal to 0. Okay. Next. So one more example for 3 cross 3 matrix. So you find determinant of so I can directly write, right? 1 minus lambda 0 2 minus 1. This is what I am writing is determinant of a minus lambda I. If I do it, I will get this one only. The only thing is you shortcut means you just subtract from lambda from the diagonal values. 0 0 4. So now you find the characteristic equation. We'll get the characteristic equation as 1 minus lambda into this 4 minus lambda. This row, this column you have to ignore, and then this multiply this, that is 3 minus lambda into 4 minus lambda minus 0 into it will be 0. Then again 2 into 0. So this is my characteristic equation. Now what will be lambda values? Lambda 1 will be equal to 1, lambda 2 equal to 3 because I am equating it to 0. this to 0 and this to 0. Directly I'll get this eigenvalues. So 3 eigenvalues are possible, 1, 3 and 4. Now for each of them, you find the eigenvector. So how will you find? So let's, for example, lambda 1 equal to 1. What will that I'll get? 1 minus 1. This matrix becomes 0, 0, 2, minus 1, 2, 1, 0, 0, is 3 into vector V. See V, now it is a 3 cross 3 matrix. So V will be 3 variables, right? V will be x1, x2, x3. This is a row vector, so transpose it to column vector. So x1, x2, 3. This is equal to 0. Now we will get equation. See, these two are 0. So x1, 0x1 plus 0x2 plus 2x3. 2x3 equal to 0. That implies 3 equal to 0. Next for this, minus x1 plus 2x2 plus x3 is equal to 0. So x3 is already 0, we know. So 2 x2 is equal to 1 by 2 x1. Okay, this is one equation. Next, last one again, x3 is equal to 0. So how will you find now? Let's put x1 equal to t. Okay, then x2 will be equal to t by 2. Then x3 will be equal to 0, already found out. So what is my eigenvector? Will be t into 1, 1 by 2 and then 0. If you want to make it an integer value, just multiply 2. So it will be 2t, it will be 2, 2, then it becomes 1, this is 0. That is the eigenvector. So for lambda 2 equal to 3, again you find out in the similar way. So this will be 0, 1 minus 2 is minus 2, then you have 0, 2, minus 1, 0, 1, 0, 0, 1 into x1, x2, x3 is equal to 0. So we'll get minus 2x1 plus 2x3 equal to 0. So that means x1 equal to x3. Then we'll get last equation x3 equal to 0. So that implies x1 equal to 0 because x1 equal to x3. Okay. So now you put x2 is a free variable, put x equals to equal to t. How will you solve this? So eigenvectors will be t 0, 1, 0. This is the eigen. Next, and lambda 3 equal to 4. What is that I'll get? I'll get this as minus 3, 0, 2, minus 1, 1, 1, and then so 3 minus 4 will be minus 1. Then 0, 0, 0. Now this is a eigenvector for this matrix. When I apply this matrix, will be equal to 0. So if you solve this, we'll get eigenvector equal to t of 1, 2, 1 and 3. Similarly, in this fashion, you can solve this. Okay. This is how you have to find the eigenvalue and eigenvector. Next, we'll see some of the key properties of eigenvalues and eigenvectors. Like the one you have seen for the rank. Similarly, this helps us to solve the problems quickly. So trace and determinant relation. Sum of eigenvalues is equal to trace of A and product equal to determinant of A. So for any given matrix, if you want to find the trace will be equal to sum of all the eigenvalues, okay, for that given matrix. And then product of all eigenvalues will be the determinant of A. Next, eigenvalues of triangular matrices. either upper triangular or lower triangular. So it will be diagonal entries. For upper or lower triangular matrices, the diagonal entries are the eigenvalues. Eigenvalues of power. So eigenvalue of a power k. For example, if I multiply a cube. So for a, if lambda is the eigenvalue for a, then lambda power k will be 3 will be eigenvalue for a cube. Similarly, eigenvalues of a universe. If lambda is the eigenvalue for a, then 1 by lambda will be eigenvalue for a inverse. Eigenvalue of transpose. A and A transpose have the same eigenvalues. Linear independence of eigenvectors. Distinct eigenvectors are independent. So what it means, I'll come to an example and I'll explain that. Similarity invariance. This means when I explained the initial concept, I said, can you convert a big matrix or a dense matrix into a sparse matrix? That is the concept of similarity of invariance, or also called as diagonalization of matrix. Now let us see example for these properties. So let A equal to this matrix. What are the eigenvalues of this matrix? The trace and determinant. What is the trace of this matrix? Trace is 2 plus 3, okay, 5. What are the eigenvalues? If I calculate the eigenvalues, I'll get 2 and 3. So trace is lambda 1 plus lambda 2. So that is the property, right? So trace of any matrix is sum of its eigenvalues. So lambda 1 plus lambda 2. Determinant of A will be equal to lambda 1 into lambda 2. That is here 6. So calculate determinant of this. This is 6 minus 0 is 6. Eigenvalues of a triangular matrix. So let us say this is upper triangular matrix. Eigenvalues are the diagonal entries, that is equal to lambda 1, 3, minus 2. So they ask upper triangular or lower triangular, you need not find using the characteristic polynomial. Just these entries will give 3 eigenvalues for this matrix. Eigenvalues of power. So if I square this matrix, for example, A square will be 4 and 9. It's again a diagonal matrix, okay? So diagonal matrix also, the eigenvalues are its, this is A square. Eigenvalues are its column, principal diagonal elements. So here lambda is equal to 2, 3. That is eigenvalues are 2, 3. When I square it, I will get lambda square. Means lambda, new lambda values are, or say lambda k 2 in this case. So it's confusing. Let us write new lambda value. So then it becomes square of this 2 power 2, 3 power 2. Next, eigenvalues of the inverse. If A equal to 2003, eigenvalues of are inverse of it. If I take the inverse of this matrix, then I will get the 1 by lambda is the eigenvalue. You can check it. So what is the inverse of this? For a 2 cross 2 matrix, you find the determinant 1 by 6 into, just interchange these numbers, and then so what will be new lambda value? Again we'll get, this will be 1 by 6 means 1 by 2, 0, 0, and then I'll get 1 by 3. So again same. These are the eigenvalues for the inverse matrix. Next, eigenvalues of transpose. So if I transpose a matrix, I'll get the same eigenvalues. For example, this. So eigenvalues for this is 1, 3. So if I transpose this matrix to 1, 0, 2, 3 like this, I'll still get the same eigenvalues because the diagonal elements remain same. Linear independence of eigenvectors. So this is key. For example, when you solve for examples, you got same lambda equal to 1, lambda equal to say 3, and lambda equal to 4. So we calculated eigenvectors for each of the lambda. Now if I take those values, all those values are independent. That means if there are, what this rule says, distinct eigenvectors are independent. Okay. So for linear transformation, you already seen. So when you convert it into row echelon form, there you already removed zeros, right? So only independent columns are coming into our final row echelon form or column echelon form. The same concept here. Eigenvectors also are same. So if they are distinct, then they are independent. We can say they are independent if they are distinct. That means what? I cannot produce another vector using one of the vectors. Say for example, I get eigenvector v1 for this and v2 for this. So using v1, I cannot reproduce v2. That is the meaning. That means what? vn and v2 are independent. When we do the linear transformation, they are independent. But if I can produce v2 using v1, then v2 is dependent on v1 or v1 is dependent on v2. That is what we can say. Then is similarity invariance. So similarity invariance means how can I convert this? For example, say the dense matrix into sparse matrix. That is the application I am saying. So for example, say that the matrix A is given. Okay, what is the equivalent matrix for this? So that it will reduce my complexity, computational complexity. This is a simple example. You may not appreciate this, but the concept is that if it's a very big matrix, how to convert this? So the rule says to create a new matrix P inverse AP should be calculated. If they have this P is calculated using eigenvectors, the eigenvectors of that matrix give me this P, and then P inverse, you know how to calculate the inverse, then A. A is the, here you find it using your eigenvalues. So we will create a matrix B. So this B matrix will have same eigenvalues as matrix A. That is the meaning. When I explain diagonalization, I will come to it again. That is the concept here. If you see this example, let us say A equal to 2103, P equal to 1101. If I take this, I will get a new matrix 2 minus 103. And if you observe here, the eigenvalues for this will be 2, 3. For this also it will be 2, 3 only. So that means what? B is similar to A, that is the similarity invariance. So I can also use B to solve the same problem, or also I can use the A, that is the meaning. So I have transformed A to B. In real world, what is the transformation? A is the dense matrix. It takes more time to compute. So if I convert it to B to a sparse matrix, which has similar thing, we'll get a same solution even with solving with B. That is the concept here, similarity invariance. So eigenvalues and eigenvectors help us there. So now we'll see what is the concept of diagonalization. So we consider diagonal matrix, and the diagonal matrix will have only diagonal elements, right? And all these diagonal elements will be the eigenvalues. Square matrix A is diagonalizable. Okay, if there exists an invertible P and a diagonal D such that A is equal to P into D into P inverse. That is what I am saying. See, if I have a big matrix, there are so many elements. Okay, there are so many elements. Okay, this goes on like this. Very big matrix. It's a dense matrix. Let us say it's a very dense matrix. Too many elements are there. There are only few non-zero elements. If I convert it to diagonal matrix means what? Only these diagonal elements will be non-zero. Rest other elements will be zero. Now, see how much computations I can save. That is the concept of diagonalization of matrix. So to convert this, there are some conditions. So how to convert and what are the steps you have to follow to check the diagonalization of a matrix. So this condition should satisfy. What is that? P into the diagonal matrix into P inverse should be equal to A. So diagonal entries of D are eigenvalues of A. So if I give a matrix A, this is A and this is D, eigenvalues of this matrix, whatever is there, okay, forms your diagonal matrix. Okay. All the eigenvalues will be your diagonal elements of the diagonal matrix. Then what is P? Columns of P are the eigenvectors of A. So if it's a n cross n matrix. So I will have n eigenvalues. Then I will have n eigenvectors corresponding one vector for one eigenvalue. This set of eigenvectors, n columns, n vectors form my matrix P. Then P into D into P inverse should be equal to A. Then only I can diagonalize this. That means A is similar to D. That is the meaning. How to find this? What are the steps procedure? Find the eigenvalues of the given matrix. Find the eigenvectors. Form D. That is using the eigenvectors of A. Then form D from eigenvalues and this just the condition. So let us take a simple example. What are the eigenvalues? So it's a diagonal matrix already. Okay. So lambda 1 equal to 2, lambda 2 equal to 3. So what will be corresponding eigenvectors? If we solve, I will get for lambda equal to 2, I will get say 1 0. This is my vector 1. And I have another vector 0 1. Now what is my P matrix? The D will be what? The diagonal matrix with diagonal elements as the eigenvalues of this matrix A. I'll get the same matrix. Okay. If you solve some more problems, you'll understand. You are getting the same matrix here, although. Then what will be my P matrix? P matrix is this vectors. So there are two vectors, 1 0 and 0 1. This is my P matrix. What is the condition? It says A should be equal to P inverse D into E. Okay. So what is P here? If you observe here, P is identity matrix, what I'm getting here in this example. Okay. So that means what? P inverse into D into P means I here. Okay, I. So it is I. So it will be P inverse D only. So this is again I inverse into D. I inverse into D is again D. So that means what? A is equal to D. Hence, this matrix is diagonalizable. Okay. So we'll solve many more examples. Don't worry. So on all the concept what you have learned, we'll solve at least some more problems. Okay. So that you get more practice. Thank you for watching. Please like, subscribe and share. We'll continue with the problem.